Today's conversation is with Joshua Isaacson. Joshua is a computational physicist at Fermilab, and his research mainly involves developing simulation tools for the Large Hadron Collider and neutrino physics. We spent some time discussing the very foundations of the scientific method, as well as his experiences in the field. We have been quite irregular in our outreach as well as publications, and we believe that it all comes with good reason. We have just initiated our undergraduate journey in university, and it takes quite a lot of effort to adapt to this new wonderful lifestyle. Nevertheless, this is no excuse for avoiding our prospect of discussing with scientists across the globe. We had, and still have, our plans to promote this platform to a diverse range of science enthusiasts, students, and academics, and hoping that our conversations could expose the scientific community to more and more people around the world, a goal that we have shared since the beginning of this journey. This all being said, we do have plans for future of our project, and we'll do our best to spread our discussions. But least of all, this channel could act as an archive for all these delightful conversations that we have with scientists everywhere. And finally, here is our conversation with Joshua Isaacson. So please tell us a bit about yourself. What are some cool aspects of your research? And maybe tell us a bit about Fermilab and the research going on there.
Okay, so first I want to thank you guys for having me. Something that I'm really excited about is I focus on doing simulations of events at these big experiments for particle physics. So I do simulations for events over at CERN in Switzerland for the Large Hadron Collider, trying to predict what we expect to see based off what we understand of physics there. And then I do the same thing for the neutrino side for predicting, what the neutrino interactions are supposed to be. And, this is something very exciting. You need to really understand the theory to then make these calculations so the experimentalists can actually use them to see whether they see some new physics or not. And one of the exciting things, on that topic at being at Fermilab is now one of the world centers for neutrino physics. So Fermilab has, like 5 or 6 experiments, and they're building a brand new one called Dune, which should be coming on in the next 10-ish years, 10, 15 years. And so it's sort of a world-class facility for doing neutrino physics. And so I got to go and look at the experiments that are currently running and see talk to the people that are working on building the new experiments. And just, being there is just so exciting, being able to see the science as it occurs, even though I'm not like an experimentalist. Being able to see these giant machines that give us this data is really cool.
Yeah, great. Maybe a bit more in depth, if you don't mind. Could you tell us a bit about your education pathway, maybe in the undergrad years, or maybe what inspired you to do physics?
Yeah, so I'll start with what inspired me because that sort of builds into my pathway.
Yeah.
Growing up, I've always been excited about math and science, and I was trying to figure out what I could do with a career with that. And my grandfather was a general surgeon. He kept trying to push me to be a doctor, and I get very squeamish around needles and blood, so I knew that wasn't my path forward. And I did biology, and it was interesting, but there wasn't enough math in it for me. I did chemistry, and there was a little bit more math, but it didn't really like inspire me. And then my junior year of high school, I have this amazing physics teacher, and we calculate like a ball rolling down a ramp off of the table, and we have to put the cup where the ball is going to land, and we have to calculate it. And if we get it on our first guess, we get full points. If we don't, we lose points for each time we have to redo it. And just being able to like write it down, calculate it, put the cup exactly where we think it's going to hit, and have it land in the cup on that first shot, something about that just was exciting to me. And so I just fell in love with physics from that point on. And it had the right balance of math, but it wasn't so formal in math that you're just doing like formal proofs. You're actually using math to do something, to explain like how the world works. And so I went into college to pursue this, knowing that I wanted to actually, do something in physics. So I went to Case Western Reserve University in Cleveland, Ohio. And this is a smaller school. And the reason I chose this was actually, it's a very good academic school, but it also allowed me to continue swimming, which is something that I was passionate about and still am passionate about. Um, I then just went through normal undergraduate, doing my classes and everything, and then went off to graduate school at Michigan State University. I did my PhD there, fell in love with event generation and, Monte Carlo tools, and actually, computing sort of became a lot more important to me at this time, and less hardcore paper and pencil math, but more, trying to solve problems using computers. And this then led me to Fermilab, where I've been since then for the past 5 years now.
Great. And sort of talking about that education pathway, what we've heard is that the education system in the US can be fairly different from the other parts of the world.
Mhm.
Could you tell us a bit about the US's education system?
Yeah, so um, I don't know much about most of the rest of the world. I have interacted with a lot of European colleagues, and the major difference between, from what I understand, between US and Europe, and maybe you guys can tell me if this is what it is in Australia as well, um, is that, you know, the US system is much more focused on generating well rounded citizens. And so we have to take these extra classes that are not focused in on physics, for example, or whatever your major is planning to be. And so I had to take class. I still had to take a biology, or I didn't have to take biology. I had to take a chemistry class. I had to take, writing classes. I had to take a history class. I had to take, a few other electives outside of physics. Um, which, from what I hear from European schools, is you apply to go to school for physics, you show up day one, and all you do is stuff pertaining to physics. And so this is something, at least at the undergraduate level, that is very different. And, you know, I'm not going to get into like which one's better. I think there's pros and cons to both of these systems, and it's sort of what fits best for you as a student trying to determine where to go. Um, then when you get to graduate school, there's other differences. So again, in the US, more well-rounded. So there's a lot of, I had to take, it's now all physics focused, but instead of taking just particle physics classes, I also have to take nuclear physics classes, condensed matter physics classes, to sort of make sure that I'm a well-rounded physicist and can, do all these different pieces. Where in Europe, when you apply to get a PhD, you go straight into doing PhD research, and you sort of learn stuff on the way, and you basically apply to work on a thesis, not apply to a university. And so there's those differences as well when you get towards the graduate level.
Mhm.
I suppose despite maybe the differences in systems, I'm wondering what advice you can give just for undergrad years, to really get the most out of it. Like, what do you think?
Yeah, so something I wish I did more myself was take advantage of research opportunities. Especially if you're really interested in getting into academia, starting early and really getting your feet wet in research is very helpful for getting you in the door to graduate schools, really helping you understand which subfields, you might be like, oh, I'm excited about, this science, but, when you go into academia, you look at some small piece of this. The way it was described to me is if you imagine a giant sphere and then you zoom in a very small corner, like piece of it, and then you keep zooming in until you're basically like, it looks flat, and then you make a tiny bump. That tiny bump is called a PhD thesis. Like, you make a very small piece improvement in a very small area. And so, just going out and trying all the different research field, like subfields within your field of interest, can really help you figure out what you are most interested in within that larger field.
Sure. And I think expanding the scope a little bit, we're wondering who you consider a scientist to be. Like, what attributes, what skills do they possess? What do you think is common amongst all the scientists that you know?
So I think amongst all the people that I consider scientists, the most important one is their inquisitive nature, like just wanting to understand something, The whole point of science, especially if you want to go into academia, the whole purpose is to advance human knowledge, to learn something that we never knew before. And I think this takes a person who really is, self-motivated and inquisitive about how the world works, how things function, to really, keep themselves driven. Um, Unlike other fields, there are branches of science where you can, these are still scientists where you go into like industry and you work on like drug manufacturing and these types of things where you work for a private company. When you get more towards the academia side, though, so there's that approach. And so you can sort of be a little less self-driven if you're going in that direction. But if you're going into academia, you're becoming a professor, you're working at a national lab, you're doing something like this. The only thing driving you is yourself. Your boss is going to tell you you need to publish papers to be a good scientist. But like my boss doesn't care what I publish papers on, doesn't care about like any of those details. They just care that I'm advancing the field. So it's a very self-driven field, and it's highly self-motivating. You have to set your own deadlines, and so a lot of people are very good at keeping themselves organized, setting their own deadlines, and these types of things.
Mm-hmm. And so, what do you think some of the like raw skills are that a scientist needs, and how do you think that we can go about improving those skills?
Sorry, what was that?
So what do you think some of the raw skills are that a scientist needs, and how do you think they can improve that over time?
So what do you mean? What do you mean by raw skills? Like
things like critical thinking, or maybe even like math or even programming, things like that. What do you think is essential?
Yeah, so definitely critical thinking is essential, and one of the best ways of improving this is just practicing solving problems. Just trying to approach a problem, trying to really think your way through it step by step. The stuff they teach you in math, a lot of math courses and the science courses already, just practicing those problems over and over again, taking a word problem, trying to work your way through it in detail. That's definitely a good way to improve critical thinking. Computing and computer programming, this is becoming huge in almost every field of science as problems become more and more complex that we can't actually do them anymore. In terms of improving your ability in computer programming, I think it's less about picking a language that is good. It's more about learning the fundamentals of how to write a computer program. Pick a language that interests you, that excites you, and just start playing around with it. Come up with a problem that you've solved on paper and pencil. Try writing it up in a computer code. There's lots of good tutorials online, tons of boot camps out there that are free to just get you the syntax. And then as you learn this, start, trying to solve the problems using your computing knowledge, and start to learn numerical methods. Like some of the most important things for me, at least in programming, especially as someone who does event simulation, are Monte Carlo methods, integration, like numerical integration, numerical derivatives, root finding. Like these are a lot of very common numerical problems, and just studying these and understanding like how the algorithms work, why these algorithms are the way they are, and sort of how to implement them yourselves. Like learning all of that helps you understand how to write an algorithm for some new problem, and gives you an arsenal of tools to address the problems as they arise.
Mm-hmm. Sure. Yeah, and we sort of touched on this earlier with motivations, but we're wondering like maybe what motivates you as a scientist, and then I suppose separate from that, what generally you think motivates people in your field, or even broader like academia.
Yeah, so what motivates me is, we have this beautiful thing in physics called the Standard Model, which describes most of the world that we see, but it doesn't describe all of it. We don't know like why there's more matter than antimatter. We don't know why there's like dark matter. We don't know what this is. We only know what makes up like 4% of our whole universe. This is like stuff we can actually see through interactions other than gravity. But like using gravity, we know there has to be more stuff out there. And so as someone who loves the physics and then later fell in love with computer programming, being able to simulate what we already understand and trying to make that as precise as possible really motivates me, because then I can go to the experimentals and look at the data that they have and be like, this is what I predict, this is what you predict, what you see. Do they agree with each other? And if they disagree, then people can try to understand what could cause this disagreement, whether it's some measurement error, just statistics, or whether there's actually new physics out there. So just trying to make the most precise predictions of what we believe how the world works is sort of what motivates me to keep working. And there's a large group of people in my field who are also motivated by the same thing. And then there's those who are actually motivated by the new physics. They like to think of what could be out there, and they come up with these crazy ideas, and it's really impressive some of the things they come up with. And they then can go and, put them into my simulation tools and be like, well, if this thing is real, this is how it would look like. This is what you would expect to see. And that's what motivates some of these people. And that's sort of on the theory side. I don't really know as well the motivation for experimentalists. A lot of them, I think, are just understanding how the world works and building things to do those tests. But I think that's a more varying, inspiration, and I don't interact with them as much on a day-to-day basis to sort of know these deeper inspirations for them.
Right.
Mm-hmm. Right. And I'm so glad you mentioned the computer science and the standard model aspect, because that's a very good segue to my next question. And that was the fact that modern physics, itself being a beautiful new mess from like the beginning of 20th century, simulations and computer simulations are even later from that. So like there's the 60s and the 70s, I assume. Could you describe to us one of the projects that you work on relating to both of to the physics and simulation, and one of the projects maybe? Yeah.
So I have a big major project that I'm excited about is a neutrino event generator. And so what this does is I try to simulate the standard model of particle physics. So at these neutrino experiments, specifically accelerator-based neutrino experiments, you have a bunch of protons, you slam them on a wall. What comes out is a bunch of pions and other particles. You then focus these then decay to neutrinos. So you create a somewhat focused, and by somewhat focused, I mean like at the point of creation, it's a few meters beam size instead of like a few millimeters at like the LHC. And you shoot, this just goes through the earth, and you have a detector nearby and a detector far away. And you try to measure the oscillations of neutrinos to sort of understand the mass of neutrinos, how they oscillate, whether they could be the reason there's more matter than antimatter. And so these neutrinos, when they hit a detector, they hit a nucleus inside the detector. And nuclei are, as you guys know, are made up of protons and neutrons, and then the protons and neutrons are made up of quarks and gluons, and it's a giant mess trying to actually simulate this. And so this is actually a big collaboration between myself, who comes more from the high energy side and event simulation, with some nuclear physics people, and we're trying to improve upon the simulations of these events, like how they're supposed to look, making sure we get everything right. Like the neutrino hits the nucleus, an electron or a muon comes out, the nucleus can break apart in various different ways. And then you don't necessarily detect the struck nucleus, but you see like the muon coming out, you'll see maybe a few protons coming out, maybe some pions. You don't really see neutrons because they don't like to interact very much either. And so trying to simulate this as accurately as possible so the experimentalists can use this to then extract, new physics and better physics understanding from this is sort of what my major project is. And so this is just a giant, I think it's up to like 20,000 lines of code right now, something like that.
It's fascinating.
Yeah, so and growing, I was working on it right before we started chatting. So
right. I suppose so. in contrast to just being excited about all that research, we're wondering what do you think makes some people leave like research science or leave academia?
Okay, so I've actually had a lot of friends leave academia, and um, just looking at data and statistics, a majority of people actually end up leaving academia.
Hmm.
And I think there's a few reasons for this. So I've had friends who love the science, they started doing the research, they're working on their PhD, and they realized that academia just isn't the lifestyle for them. They love the physics, but the day-to-day aspects of the research just wasn't exciting them anymore.
Hmm.
And so they decided to branch out into other things. A lot of them gain huge skills in data science and they go, oh, well, I can apply this elsewhere, and they leave and they're more interested in the statistics and how you handle this than in the physics that comes out of it.
Hmm.
Others just get towards the end of their degree and they look at the field of academia and they compare this to the private sector and they see the difference in salaries, and then they decide they'd rather make more money than continue down this academia approach, and they leave the field to make money. I have friends who have left to go work for Google and these types of companies, making like 5 to 10 times what I make, doing work that's not drastically different than what I do, in terms of they're just also computer programming. But I think another one of the major aspects of people leaving is just the lack of permanent positions. If you want to be a permanent position, like I still don't have a permanent position. I'm still trying to figure out what my next step is. And this, I think, is one of the driving causes of people leaving the field, because universities aren't hiring as many people as they used to, because people either aren't retiring or there's just not as much funds going into paying professors. And so a lot of people just can't find that next step. They get stuck in as a postdoc for a very long time. They get tired of being a postdoc. Life moves on. They start having families and things, and a postdoc lifestyle is just not a good place to have a permanent position forever. You sort of want to get that salary increase to make your life meaning, to do the things you want to do. And I think this is also one of the big reasons people leave. It's just a very tough competitive field and there's very few permanent positions.
Right. You earlier mentioned that you've been involved in both CERN and Fermilab.
Yeah.
And we want to know how large-scale international collaborations in those institutions are, organized and completed. How do scientists get involved in these projects, and perhaps maybe how can students get involved along with them?
Yeah, so I'm not technically, so these collaborations are the experimentalists, so I'm not a part of the collaboration, but I work closely with a lot of people involved, and I sort of know the process for some of them. So for like CERN at the LHC, if you want to join those collaborations, you have to do a service project, which is like a 6-month project doing things for the detector, whether this is software or hardware, like building a new component that's going to go into the detector, or developing new software to be so that the measurements are quicker so you can record more data, or just improving other aspects of the detector in other ways. And you work on this for 6 months to a year roughly. I think there's a panel that decides when it's been enough, and this is called your service work. Once your service work is completed, you get your name on the list of authors, and every single paper that the collaboration writes, you're on that. And then you have your own individual analysis that you're doing on top of that. That's sort of like your work outside of just the service work that you're doing. I don't know if this is the same for every collaboration. I don't know, for example, how Dune gets the people on the list. But in terms of students and other people getting involved, there's tons of internships out there. Fermilab has a ton of summer internships. All the U.S. national labs have ton of summer internships. Most of the universities have summer internships. I don't know what it's like in other countries, but getting involved in research early on, really going to the professors, talking to them, being like, I'm excited about the research you do. Like, first look it up, see what they do, make sure you actually do like it. say, is there any way I can get involved? And they'll tell you yes or no. They'll tell you what stuff you might have to work on before you can get involved, but just talk to them, let them know you're excited and see. And, I've worked with a few undergraduates. I recently had an undergraduate I mentored for his senior thesis, and we've actually published a paper now together. So there's this pathway where you just talk to people, put yourself out there. Even as high school students, if you're interested, you can try to find internships. These are much fewer, and a lot of them are a lot of grunt work, but there are still opportunities to get involved at research even as a high school student. And all of these can just help open those doors and get you into these collaborations if that's what you're excited about.
And at these large organizations, right, so CERN, for example, Fermilab, I'm curious because there's so much, how do they, as a collection, prioritize research questions? How do they choose? And I suppose, and what are some of the driving questions, say, at Fermilab?
So it sort of then breaks apart into different sections, right? If you're talking about how the experiments like Atlas and CMS at CERN function, the way these work is they have what are called topical groups. So this is in terms of particle physics, like standard model physics, Higgs physics, top physics, BSM physics, these types of things. They have these groups, and you become a member of these topical groups, and they have meetings every so often, and you talk about what searches you're involved in, what analyses you're doing, and people then discuss and figure out which ones they should continue with, which ones they shouldn't. This gets political. I'm not involved in these, so I don't know all the technical details, but I know they break it down into smaller and smaller groups. So you're really only meeting with 10 people at a time that you're really working with on the day-to-day basis. In terms of if you're talking about institutional wise, Fermilab is broken up into a bunch of divisions. So there's the theory division, the particle physics division, the neutrino division, the scientific computing division, and each of these have their own division head, and then these divisions are then further divided into departments. So the theory division is divided into particle physics, astrophysics, and now quantum information science. And so then it's not there's not the head of Fermilab says these are the things we're going to do research on, and then they tell everyone what you're going to do research on. It's much more self-motivated. You say what you're interested in, you find a group of people who are interested in it, you get enough people who are interested in this, and you can then push it up the stack and actually get something done. So it's more of a bottom up than a top down, at least in my personal experience and how things get organized.
Sure. And you mentioned earlier how the academia lifestyle might not be for some, but I'm curious what the actual lifestyle looks like. I suppose, what does a day in your life look like, or the day in a scientist's life?
Yeah. So a day in my life is, I wake up, there's the archive, which is a place where people post preprints. I don't know if you guys have heard about this before, but people post the articles there every day. So that one of the first things I do is I go through all the articles and all the subjects that I might be interested in. So I go through, for example, myself, I go through quite a few. I go through the particle physics phenomenology, the high energy physics theory, high energy physics experiment, high energy physics lattice papers. So those are all more pertaining to my field, to see sort of what people are up to. And then I go through the machine learning ones for both computer science and statistics, to sort of see what new techniques might be developed in terms of machine learning approaches to apply to my work. So I go through all these, I sort of skim through all of them, find the articles that interest me. I read through those in more detail. And then the ones that are really interesting, I bookmark them, put them somewhere to come back and really analyze later. And then I sort of get to work on whatever I'm working on. So, I have a bunch of problems in my generator that I'm trying to solve. And I sort of pick the one that's exciting me the most at that point in time, I guess is the best way to describe it, or I guess annoying me the least, whichever way you want to put it. So I just sort of figure out which, because I have like 50 things on my to-do list to do, and I just sort of find the one that sounds the most exciting at that time to work on. And I start working on this, have discussions with some colleagues on, maybe problems that I've come into to trying to do this, or asking them to help with some aspect of it. And, we have discussions on where to go. So I have, 1 to 2, 3 meetings sometimes a day where we talk about the physics. And then I also spend some time working on writing papers. It all depends on where I'm at. I do a bunch of work, I write a bunch of papers, and it sort of like goes back and forth to where I'm spending more time on trying to do the physics, or I'm trying to tell other people the physics I've just done in terms of writing papers. And then there's always all, less frequently, there's all the service work that you have to do, such as peer reviewing other people's articles, talking with your boss about life, filling out your timesheet, like all the bureaucratic stuff, that takes some time, but that's usually very small compared to the rest.
Is it fair to say that you have a fair amount of freedom in what you get to do?
Yeah. So, and I think this applies more as a theorist than as an experimentalist. But this is just from my personal experience, and it also depends on where you're at and who your boss is. My boss and most of the senior people in the Fermilab theory department are very open to letting us postdocs explore. And I think as postdocs, sometimes you get stuck where, as a postdoc, you're working technically for someone. Like, I'm not a professor. I'm not the one, who gets the grants. I'm not the one who brought in all the money. So at some universities, postdocs are more told this is what they need to work on by their like boss, like the person who actually is paying them. And so, but there's still like a ton of freedom. If you have an exciting idea, most people are open to listening to that and allowing you to pursue it, at least to some degree, because that's really how academia works. No one knows what the answer is, because if we knew what the answer is, then we wouldn't be, it wouldn't be research anymore. It'd be, like a homework problem, for example.
Yeah. And so moving away from this topic now, we're curious about some of the alternatives to academia. So you mentioned that some of you, people like moved to places like Google and so forth.
Yeah.
But so what do you think are some of the pros and cons to the alternatives, say industry or working in government or something?
So I think most of it boils down to, so there's a few like hard cut pros and cons. If you go into academia, you're going to be making less money more often than not than people who go into industry. So this is like a major con of academia, and a major pro of industry, is salary. I think a major pro of academia is, we were just talking about this freedom. You have this flexibility to do what excites you and not what some company tells you should be exciting to you. Like if you go to work for like Google, they say, we need to improve this algorithm. It's not fast enough. And your job is to improve that algorithm. Even if you get burnt out and start hating it and you can't stand that looking at that code anymore, if you don't work on it, they're not going to pay you for doing your job, because you're not doing your job. For me, if I get burnt out on some part, I can always pivot to something else that's exciting me at the time. So this freedom is a major benefit of academia. For me personally, one of the things I've wanted to do is give back to the world and the community. This is sort of, why I want to eventually be a professor. Like, I'm happy at a national lab, but my ultimate goal is to be a professor, because, you can train, you can, advance human knowledge in areas that people haven't done before, and you have more flexibility in academia. Not saying that this doesn't happen in industry. Like, this happens all the time in, certain parts of industry. Like the pharmaceutical companies are major innovators and really pushing forward our understanding of how drugs work. But for the most part, I think most of these advancements, especially the less critical ones that are driven by financial decisions, you have that flexibility in academia. and this ability to become a professor and really teach the next generation, to inspire people to go out and improve the world, make the world a better place, help us understand more. You have like, if that's what you're excited about, then academia is the place. You don't really have that same mentoring experience that you can get as in private industry.
Yeah, and sort of taking it on the same note, is that what are some other unpleasant parts of being a scientist in general, both in academia and in industry? What do you think?
Unpleasant parts.
Because what we hear a lot about from every scientist that we talk to in sort of like a selection bias way is scientists who are in academia, if they stay in academia, they are perhaps happy with their jobs. They're happy about their research. But what we can't usually hear enough is the unpleasant bits.
Yeah, so I don't know the unpleasant bits of industry. I sort of just imagine those unpleasant bits to convince me that I've chose the right path. So I'll just focus on the academia unpleasant bits. So for me personally, the whole publish or perish aspect of academia is really a major turnoff to me. And so this is where it's now like, if you want to advance your career, it doesn't matter how exciting or how cool your work is. It really boils down to how many papers you publish and how many people cite those papers that you publish. And you see this aspect where people publish like 50 papers, all of which aren't really huge advancements. They're all just minor steps, and they get cited a bunch and they get promoted very quickly. And then there's other people like me who do much harder problems that take longer to solve, and you get fewer publications and fewer citations because it's a smaller subfield. And this then slows down the progression, and you get sort of less recognition for your hard work. So that's something that I think is a huge downside. Other unpleasant things is, as most people will tell you, is all the bureaucratic stuff we have to deal with. Like, we go into academia to do research, but then when you become a professor, you have to go to faculty meetings and discuss how the university needs to be run, and you have to do grant applications. So you have to actually apply for grants and money, and these types of things like grant writing. I actually just finished working on a grant proposal, and these are some of the least enjoyable things you can come up with. You have to tell people why, you have to tell other people who don't necessarily understand the physics why what you are doing is worth giving you, $5 million for 5 years to continue working on. And you can't just be like, you can't actually just do the physics. You have to actually spend weeks trying to get the messaging right to the people who actually decide who gets funding and all of this. And it's just a nightmare, trying to write grant applications, making sure it's polished the right way, geared to the right audience. It's just not fun. I can't think of any other like major unpleasantness. Sometimes there's way too many meetings that you have to go to. You know, sometimes there's, we have a ton of talks, and sometimes the talks are amazing and exciting. Sometimes they're boring. And it's less so now that we're remote, but when we were in person, people would come around and be like, hey, this talk's about to happen. Do you want to come? And if you go, oh, I'm not interested in that talk, you sort of feel like a bad person. So you go to the talk, and then you're sitting in a talk that, isn't interesting to you, and you were really deep in your problem and really grooving with solving it. And, you just break up your whole flow. Mm-hmm. So, but that might just be a personal thing for me.
And on the topic of publish or perish, I'm curious what you think, who actually does the selection that causes people to perish, right? Because I imagine that, just trying to dish out heaps of papers, I imagine that it would lower the quality of them. As you said, they're not actually they might not be doing interesting things, which is good for nobody, right? So who gets to decide?
And yeah, in that regards, I'd like to mention a case of I'm not sure if you've heard of it, but the Jon Hendrik Schon from the Bell Labs. It's a famous story. It's the story of publish and perish, exactly what Carlos says. what is it that causes? Because if the quality is bad, you know,
Yes.
what is the actual problem?
So the way I understand how this came about is that the bureaucrats, the people who are in charge of hiring, right? So the hiring process for like faculty positions and determining whether you get tenure or not has many steps involved and many people involved. So, they'll like to get a position even started, the professors say, oh, we really need someone to do research on X, and we need another professor to help teach courses. They'll then go to the chair of the department and be like, look, we need a new professor to do X. And you have to convince them that it's worthwhile. The chair then has to go to HR and the dean of the university and be like, look, my department really needs X. Do you have money to help start this? And they'll then decide and debate. And then if they say yes, then it goes all the way back down. Then they can finally post the position. You then have to go through. And since it's so hard to get these positions, there's usually like, 50 to 100 people applying to each position. And you can't just you can't just spend, a day on each person's application. That's just not feasible. And so you have to have some way to quickly go through them. And I think this is sort of part of where it comes from. People try to go through applications quickly. They look at sort of these metrics to try to determine who should be brought in for interviews and who should really be thoroughly vetted. And so this is, I think, part of it is sort of in the fact that, there's a lot of people vying for a few positions, and there has to be some quick way of narrowing down this list to a small selection of candidates. And then when you get to tenure, and trying to apply for tenure positions, you have to sort of justify to the people above you that what you do is important, is meaningful, is impactful to the field. And the bureaucrats want like hard numbers, like the people at the university who write checks to people and pay people want hard numbers as to why you're actually important. And so things like how much grant money you bring in becomes important. There's this thing that physicists actually developed called the H index, which is basically how many papers you have published that have at least that many citations. So if you have like 12 papers published, but 10 of them have 10 citations and the other two have less than 10, your H index would be 10. And so this is sort of a metric that people use to give numbers to people who don't necessarily understand the physics. So I can't just, they can't, the physics department can't tell the dean of the university that the physics you're doing is super exciting because X, Y, and Z, and go into the rigorous details of what you're actually doing for research. They have to tell them using hard numbers that they can understand, like they've written this many papers, they're getting this many citations, it's really, people are really excited about the work by looking at how many people are reading and building on their already completed work. They're an important aspect of the field. And I think this is part of where this publisher Paris comes from as well.
Mm-hmm. And another unpleasant aspect that we've sort of heard a lot talking to scientists is the imposter syndrome within the scientific community.
Yeah.
So people sort of feeling they're not competent enough compared to their colleagues maybe, or the peers around them. What is your input on that?
It's definitely a thing. I actually suffered from it during graduate school and periodically suffer from it still. Where I just feel that I'm not at the place I need to be. And it's a very real thing. It happens a lot more in, like, people have done studies on this, and it happens a lot more in minority groups and women in science, just because there's fewer of them. And so they don't have those role models who can be like, look where I'm at. I'm, here, and I'm saying you're doing a good job. Like, a white male professor telling a minority student or a female student that they're doing a great job doesn't have the same impact as a minority or a female professor saying the same thing. At least that's what I recall from reading about the research. And it's a major deal. People suffer from it all the time, just not getting that feedback. It's very hard you see what you see is you see your professors and you see how good they are at doing research. You see the more senior people and how good they are at doing research. You see that one person who just put out a really exciting paper that everyone got super excited about, but then you think about your last paper and you didn't stir up the same excitement. And these things just all play into the fact that maybe you're just not as good as they are. And so there's like all these small things that just build on each other. It's an important thing, and I think the important thing to know is that if you make it as a graduate student, or you make it as a postdoc, or you get to professor, like the people choosing who goes into these positions know what they're doing. And so if they tell you, and this is what I tell myself, that if they think you belong there, then you are good enough to belong there. And I try to tell myself and remind myself this every day, but those feelings still creep in that maybe they just didn't see it and you're doing a good job faking it. But so it is this thing that you're constantly battling with yourself.
Right. And so next question is, again, just trying to get to a more positive note, I suppose, from all the unpleasant aspects. We want to ask about science communication. So there seems to be a very dire need for it. I suppose that's exaggerated more, recently with COVID, right? And you see all the misinformation about vaccines and so forth. So we're just wondering what the attitude is within academia, what they think the responsibilities of scientists may be to enable science communication.
Okay, so this varies drastically from person to person. And people have different views on this. And like outreach, there's some professors who think that they don't need to do the outreach, other people will handle it. And then there's those who are very excited about talking to other people, explaining to the community what they're doing at a lower level, and these types of things. Like personally myself, I think outreach is one of the key cornerstones of academia. And I think a lot of the higher ups, the more senior people, tend to forget about this aspect. They get so drawn into their research that they don't go and talk to people to explain why their research is exciting. And so like some of the things that also make it hard is that there's all this terminology that gets built up, and you're talking using this lingo of your field that other people don't necessarily understand. Like I would say like QCD like all the time, and jets, and other thing like NNLO and these other terms that have very, very significant meanings to me, but probably don't mean much to either of you what those terms are. And so trying to take the language we use on a day-to-day basis and break it down to a level that someone not in the field can understand is very, very challenging. And I think this is one of the biggest hurdles to actually improving scientific communication, is actually improving, giving courses to graduate students, especially on how to communicate with the public. And I think it's sort of viewed as, if you're interested in this, then go ahead and you can get practice doing it. But it's sort of like, if you don't care to do this, then we don't, it's not going to affect your future career. At least at most top tier research institutions, they care about how much money you bring in and not how many people you educate on your research. So, but this is something that I'm actually passionate about. This will be my third year where I'm going to talk to US Congress about why it's important to fund particle physics. So, I go and I talk to them, and I don't necessarily talk to the people in Congress, but I talk to like their staffers, and I have to explain to them like why the research my field is doing as a whole is important for the US to continue to fund, and like why we matter. And I can't explain things at, my day-to-day research level that I would talking with a colleague. I have to sort of break it down to someone who may or may not have studied any physics in their entire life. And so I think just getting out there and getting this practice is important. But as the saying goes, it's much easier to create a falsehood than it is to prove that falsehood false and to like do the truth. Like I can say something completely wrong, and then for you guys to prove me wrong would take way more time for you to do than it took me to just say it in the first place. And I think this is a major issue that we're seeing, especially with social media and YouTube and these types of things. It's just much easier to get your false information out there. And then, if the scientific community were to go one by one and tackle these, they would spend all their time just trying to tackle them. And so it's sort of this balancing act that you got to do as much as you can, but you can't sacrifice everything else that you're doing work on. So it's a tough thing, and I don't know what the answer is.
Yeah. So I have a philosophical question about physics. And this is coming from an outside, right? Because like Marnie's a physics person, whereas I love biology. So it's very. I'm curious. Why do you think maths can explain how things work? And like very broadly, why do you think it can explain how the universe works? Like, how does that work? It's like fascinating that it's like something that we can write on paper and do computers can explain so much.
So there's actually a very deep tying in between mathematics and physics, and one of the big things is Newton, right? This is like one of a great example of this. Newton was sitting down writing Principia, trying to sort of lay the foundations of physics. And with the math that was available, he couldn't do it. And so he actually ended up inventing calculus, and there's lots of these one-to-one correspondence to it. There's tons and tons of things in mathematics that don't describe the real world. And basically, the whole purpose, at least the way I view the field of physics, is to come up with a mathematical description of how the world works, right? Like that's the whole goal of the field. It's not necessarily that all the math can be directly applied to physics. It's how do we take math and mathematical modeling and use it to describe what we see. And that's sort of how it builds. They sort of build on each other. We observe some phenomenon, we see some trends, we try to understand like why that trend is there. For example, like you'll measure velocity versus distance, and you'll see there's this linear relationship, and you'll work out why this is, and you'll say, oh, they're related because it's the velocity of the integral of your velocity is your distance, et cetera, and you just try to build the math to explain what you see. So I think it's not really that math happens to explain physics. I think it's that we try to find the math that can explain the physics. So it's sort of like we're taking both pieces and building, like we have data, we have math, how can we get them to work together?
Sure. All right, this is awesome.
Yeah. I mean, and this happens in other fields, like in chemistry and biology, especially as you get more towards like computational aspects, there's a lot of math in it, right? There's a lot of differential equations in biology as you get into like how cells actually function, like activation of cells and these types of things get into differential equations. So it's not that physics is unique into this, it's just physics has a much longer history of using these more complicated math, but the other fields are starting to bring it in more and more every day.
Sure. Cool. We've reached our last question, and what we like to do is for every scientist, we want to assemble a book of quotes, like of some words and wisdoms, like a sentence or two that you can add. So this can be about science, can be about life in general, and like the quote, it can be yours or it can be something that you've read from a book that you like. It's very broad.
Yeah, I'll have to think of something then.
Yeah,
this is sort of putting me on the spot.
Yeah.
I wish I could have prepared for this. Okay, let me give it a shot and we'll see how this goes.
Sure.
So, my personal philosophy is that, that your career is something that you're going to have, and finding the one that really inspires you and makes you joyful and allows you to enjoy day-to-day life is the one you should pursue, and you should strive to reach excellence in that. That doesn't sound good, never mind.
No, I was enthralled. You had me from the start.
I don't know a good one. Yeah, I just think like whether you decide to follow science, academia, industry, whatever you want to do, just find the joy, like find what in the world gives you joy and pursue that. I think that's sort of, the whole purpose of life, right? Is to figure out what excites you and go and investigate it and, enjoy.
Sure.
That's great.
Sure. We'll go with that.
Yeah.
Yeah.
Look.
I'm not very inspirational or good at coming up with.
No, it was
quotes.
beautiful. Look, so yeah, we reached the end of our questions. Honestly, it's been really great talking. It's been great.
Thank you. Yeah,
thank you.
I've enjoyed chatting. Yeah, as I say, as I was saying earlier, outreach is something I'm passionate about. So getting the opportunity to do this is something I was excited about to do and chat with you guys. So I really appreciate you guys again having me on here.
Thank you. Cool.
Thank you. So also good luck for both of you starting school, right? And I hope it goes well. And if either of you have questions, or if any of the people who view this have questions, I can give you guys have my email. You can give it to them. You can put it in like the description down below. and if you have questions, send me an email. maybe not put my work email in the description, but contact you guys, and you guys can give it to me, so you can filter people.
Sure.
That's great.
Thank you. Okay.
Yeah.
Well, I suppose on that, we should head off now. Again, thank you so much.
Thank you.
Yeah, thank you guys again.
Cool.
All right. Bye, guys.